Welcome to perhaps class number 104, and today we're talking about atmospheric boundary layers over mountainous terrains. And the reason why this is interesting is because when you think about boundary layers, we almost always think about like wind tunnels or water channels or airplanes or wind turbines and buildings. But the Earth is pretty much just like one big surface with air going over it, so there's a massive boundary layer. And we're in a boundary layer. So, for example, where you are now listening to this, unless you're flying on a plane, you're almost certainly going to be inside a boundary layer. And as you go further out or further up, you get into a faster moving flow and then eventually into the outer part of the boundary layer and into the free stream flow. So mountains, for example, they provide effectively massive surface roughness and a lot of topography to alter what's happening in this boundary layer. So when you look at it like this, it's a very interesting aerodynamics phenomenon because, as we'll see in this paper, we're going to be looking at not only aerodynamics but thermodynamics, and thermodynamics has a major impact on the atmospheric boundary layer, which is often overlooked in regular boundary layers because often the thermodynamic side of a boundary layer is fairly non-existent. Like there isn't really much heat flux, and one surface usually isn't very hot, or the boundary layer isn't very hot compared to the other surface, and etc. So there's not really many thermal differences. That's not the case here. So it provides a very interesting, a different angle that we can look at boundary layers from and a different influence. So to look at this, we're going to look at a paper called Exchange Processes in the Atmospheric Boundary Layer over Mountainous Terrain. And this is open access, so you can find it in link in the description. So let's start off here. They say that the study of Earth-atmosphere exchange processes plays an prominent role in meteorology and in many related disciplines. For example, climate science, hydrology, cryospheric science, and agricultural science. Exchange is the transfer of fluid properties through a surface, and it may occur either at the boundary of a fluid, so for example, the Earth and atmosphere exchange, or across an imaginary surface within a fluid, for example, between the atmospheric boundary layer and the free stream atmosphere, so between two different velocities, for example, of fluids, or even between different fluids of different densities or pressures or even temperatures or different chemical compositions. Transport is a synonym for exchange, while flux denotes the rate of exchange of a quantity per unit area. So these are all basic terms. Exchange processes at the land surface and within the atmospheric boundary layer are represented in numerical weather predictions and climate simulation models by empirically tuned and inherently uncertain parameterization schemes. So what does this mean? It means that these processes that we look at the atmospheric boundary layer and the effects on the climate and our weather and etc. are all effectively modeled through empirical equations. There are some theoretical equations as well, but empirical equations play a massive role, which means that a lot of things that should be defined are really just grouped together, and that provides a major benefit in terms of being easier to calculate, but it also makes it less accurate usually. So the parameterization of Earth-atmosphere exchange emphasizes the role of small-scale turbulence processes and uses methods and concepts for boundary layer meteorology. While this approach may be appropriate for over flat and homogeneous terrain, it provides overly simplistic when applied to it proves overly simplistic when applied to exchange processes over mountainous terrains. So these mountainous terrains are far more varied. So using empirical data that has been gathered over flat terrain doesn't necessarily apply to mountainous terrains. So in a nutshell, from a mathematical point of view, you're using a data set which you've collected in a certain set of conditions and trying to extrapolate it to another set of conditions, and often extrapolation proves very inaccurate. So to look into mountains, the flow over mountains, you need to have a more accurate data set. So you don't need to extrapolate and more likely interpolate instead, which is better. So mountains impact the atmospheric flow by modifying synoptic scale advection processes and generating planetary waves. So what does this mean? First of all, synoptic scale advection. Synoptic scale means at the atmospheric level, so like on the order of about 1,000 kilometers or almost 1,000 miles. Advection is very similar to convection, but they're slightly different. So you can say everything that is advection is convection, but not everything that is convection is advection. So advection is just the process of transferring some property, whether that's mass or temperature or pressure or density or whatever, between two systems, between like at one location to another location. You're taking one location and moving these properties to another location. That's advection. The difference with convection is you not only have this advection, but you also have the reverse loop as well. So, for example, water is a fairly good approximation for convection, where you have, rain, which then the water falls to the ground. You then have evaporation, which brings it back up to the sky, and then the cycle continues. So in that particular case, that's a convective cycle. But advection would be like the rain just falling, and then another advection cycle, another advection part, sorry, would be just evaporation. So those two together would then make the convection cycle. So that's what this means by modifying synoptic scale advection processes. Now, generating planetary waves, this is actually massive fronts, effectively, like weather fronts kind of thing, on a 1,000-kilometer scale. So that's what a planetary wave is. And these produce mesoscale organized motions, and they alter microscale turbulent mixing. So in other words, the advection and these planetary waves give rise to these weather fronts kind of thing, and differences in pressures and temperatures, and also change even the microscale turbulent mixing. So when you go to like our kind of level, like 1 meter or 2 meter scales, you have different mixing going on with the turbulence. So the spatial scales of the orographic impact are dictated by landforms ranging from like 100-meter scale to a 1,000-kilometer scale for mountain ranges. That, for example, 1,000 kilometers is actually also known as a megameter, if you were to follow the kilometer and megameter idea. So orographic impact is again relating to the 1,000-kilometer scale range. So the relevant temporal scale ranges from seconds, so this is for turbulent bursts in stable stratified flows, to tens of minutes for the turnover time for a large turbulent convective eddy, to a few days for frontal passages over major mountain ranges. So, for example, in podcast number 2, I believe it was, when we were talking with Luca Caracoglia, and we've also done some other podcasts on this topic, which is to do with storm downbursts. So these are when you have a lot of fluid moving down, so a lot of air coming down, and actually hits the ground, and it makes this like concentric vortex ring, and then that moves out radially. That happens on a scale of about 10 to 20 minutes, and that's one of these scales here, but they can go from seconds to days, depending on what the climate phenomenon is. So a further layer of complexity results from the fact that besides orography, other land properties feature small-scale variability in the vicinity of mountains. So, for example, we can have land coverage, vegetation, soil moisture, and the presence of water bodies all change how flow moves over mountain ranges, along with temperatures and these planetary waves, etc. So it's a very complicated process. It's not just having a smooth surface and flow going over, and you get like small little Thomas slitting waves that then break down to turbulence. It's far more complicated than that. So prospects for progress in understanding exchange processes over mountains rely on 3 elements. The first is a dense measurement network that exploits remote sensing platforms, and targeted observations are needed to map the state of the atmosphere near mountains in 3 dimensions. So in other words, you need to gather a lot of data. Second, it is necessary to make use of a high-resolution numerical weather prediction model using discretization methods with sufficient accuracy and stability over steep terrain, and appropriate subgrid scale processes, and initial and boundary conditions that represent the multi-scale variability of the atmosphere over and near mountains. So in other words, you not only need to have good data, when you come to numerical simulations, you need to have appropriate discretization methods, including the proper approach for subgrid scale resolution. So when you have, let's break this down to regular CFD simulation, let's say you have your mesh. And this is what they do with climates as well. They mesh, like they actually have a simulation of the part that they're looking over. And the mesh is only so fine. And inside the mesh, in these little cells, you can't actually properly model what's going on there for a lot of different parameters. So, for example, if you're looking at RANs, you can't really model the turbulence properly inside these cells, let alone between cells. But anyway, that's another story. So coming up with a proper subgrid scale approach is paramount. The third element that you need to accurately understand the exchange processes over mountains is that it's essential to achieve a better conceptual understanding of the processes at play between the synoptic and microscale ends of the spectrum. So in other words, what's happening at the large scale and what's happening at the small scale. So the present contribution of this paper focuses primarily on this latter. So what is the system in general? What is the theory? And in particular, on the thermally driven dry processes. So again, the thermodynamics aspect. So this paper is actually 32 pages, so they pretty much wrote the life story. I'm not going to go through the entire paper in this podcast. We're going to break it into 2 podcasts at least because it is really big, as you will see. So let's move on with the first part of this paper, which is understanding the atmospheric boundary layer over mountains. So the daily cycle of the surface radiation and energy balance leads to alternating phases of heating and cooling in the lowest atmospheric layers. So in other words, depending on which part of the day you are or night, you can get cooling like where we are or heating. Where the terrain is flat and homogeneous, stratification and buoyancy effects enhance turbulence during the day and suppress it at night. So that's interesting. On flat surfaces, turbulence is greater during the day than at night, effectively, what they're saying. Where landforms or land coverage is spatially heterogeneous, the daily cycle of the atmospheric boundary layer is not only affected by turbulence enhancement and suppression, but also by the baroclinicity due to different heating and cooling. So baroclinicity is a macroscopic idea where it happens when you have the lines of constant pressure in the atmosphere are not aligned with the lines of constant temperature. So they're at a different angle. So for example, let's say you have your table in front of you, and 1 centimeter from the top of the table, you have one line going across horizontally. And that is of a pressure of, I don't know, let's say 1,000 pascals, just for demonstration. Then you go up another centimeter and it is now 2,000 pascals. So these are all horizontal. But if you have isothermal lines, they're not horizontal. So they might be at 20 degrees. So you might go up, you have to go at a different angle to start reaching like 21 degrees Celsius or 22 degrees Celsius. When they're at a different angle, this results in baroclinicity. And this can drive different weather patterns. So in the vicinity of mountains, breeze systems respond to thermal contrast at the scales of an individual slope, of a valley, or of a whole mountain range. So in other words, you can get local winds happening because of just different local points, for example, just a slope or just a valley, or even the entire mountain range. So you have all different scales. That's what makes boundary layers over mountains so interesting. It's like having a table, but all different surface roughnesses. So thermally driven circulations typically have the maximum intensity near the ground. This is where pressure gradients are strongest. So in other words, the pressure changes most near the ground, and this drives a lot of different winds, which are thermally driven as well. These flows, in particular slope and valley winds in their fair weather conditions, are prominent features of the atmosphere in mountainous regions, and together with turbulent mixing, they control the exchange processes. Another difference between the atmospheric boundary layer over flat, homogeneous terrain and the atmospheric boundary layer over mountains is that, as they're going to go through in the following sections, strong horizontal gradients are relatively common in the latter case, so over mountains. For instance, in connection with nocturnal valley exit jets, diurnal flow along curved valleys, or mountain venting above mountaintops. In other words, let's go through this. What they're saying is that in the mountainous zones, you can get very strong horizontal gradients in different, for example, in temperature or pressure. And these often drive wind patterns. So, for example, in valley exit jets, so when you have a valley and you have a wind coming out of it faster than the free stream velocity, diurnal flow along curved valleys. So, diurnal flow is when the flow peaks and troughs during the day. One peak, one trough, or mountain venting above mountain tops, which is when the flow goes up and then it goes over the mountain tops. So consequently, it may be inappropriate to assume that the vertical exchange is much more efficient than the horizontal one over mountainous terrains, because you do get these winds being driven through horizontal gradients in pressure and or temperatures, which you don't get in typical boundary layers over, let's say, a flat plate. So let's talk about the surface energy balance in complex terrain. The atmospheric boundary layer is commonly defined as the part of the troposphere that is directly influenced by the presence of the Earth's surface and responds to surface forcings with a timescale of about an hour or less. The most important driver of the temporal and spatial variability in the atmospheric boundary layer is the surface energy balance. So let's talk about the surface energy balance. In figure 1, they have a bit of a hill, and on one slope they have wind going over it, and they have different energies coming in and out of the surface. So they say in figure 1, ideally the terms of the surface energy balance include net radiation, sensible and latent heat fluxes in the atmosphere, and ground heat flux. So let me discuss what these are. First of all, the net radiation. This is the net radiation that comes from our sun, effectively. So when the sun's rays hit our Earth's atmosphere, there's some of the radiation that gets reflected away, but some that gets in, as we all know. The bit that gets in and through to the ground, like our ground level, is the net radiation. So that will go into the Earth. Then you have the ground heat flux. So this is the heat that's going into the ground from radiation and or anything else. Then you have sensible heat flux, which I'm a fan of because I don't like heat flux which aren't sensible. They should be sensible. So this is good. So a sensible heat flux is just the radiation that gets radiated out of the ground upwards. And then you have the latent heat flux. And latent heat flux comes from typical thermodynamics. So if you know thermodynamics, you've heard of the term latent. And this is when you are changing a material from one phase to another. So whether that's going from solid to liquid or gas or plasma, to do that, you necessarily won't get a change in temperature, but you have to still give it more energy to break into that other phase. So break the bonds effectively and go into the other phase with more energy. You won't get a change in temperature there, but then when you put in more energy, we will then start to get a change in temperature. So you have those 4 different energy fluxes: the radiation, the net radiation, the ground heat flux, the sensible heat flux, and the latent heat flux. And depending on the differences in these, you'll get either more energy going into the ground or less energy going into the ground. And in figure 1, they have this graph shown here, and they show that the amount of energy effectively going into the ground is more than coming out. So there's this this part that isn't being that they don't really understand, like where is the additional little bit going or coming from. I should also mention with this figure, I did a little bit of research on this, and this is just idealized. There is also the amount of energy that is being used and or given out by vegetation. So that's also another potential energy source there, an energy heat flux there. So measurements usually indicate an underclosure of the surface energy balance. So in other words, underprediction, even over homogeneous and flat terrain. This means that the sum of the surface turbulence sensitive and latent heat fluxes is less than the available energy, so the net radiation minus the ground heat flux. The potential explanations are still ongoing. That's why I looked into this topic a little bit more. To illustrate the significance of the surface energy balance closure problem in complex terrain, figure 1C shows the energy balance for the lowest layer at the valley floor site in the Riviera Valley in southern Switzerland. So this has a graph, and they have the time of day from 0 hours to 24 hours, and they have the amount of heat flux or energy flux throughout this period. And interestingly, at night, there's almost no heat flux. It's like 5 or 10 watts per square meter. However, when you get to about midday, this jumps up all the way to like 500 watts per square meter, so it's a lot. So they say the difference between the available energy and the sum of the heat fluxes in figure 1C largely exceeds the uncertainty that can be attributed to measurement errors. Therefore, underclosure due to measurement errors, often advocated for ideal sites, can be excluded in this case. For this particular location, so this Riviera Valley in South Switzerland, vertical advection accounts for a considerable part of the underclosure. So in other words, the advection part of moving heat away from the surface can potentially make up for this unaccounted energy. So let's move on to daytime thermally driven winds. The small scale end of thermally driven baroclinic circulations over mountainous terrains correspond to slope winds. Okay, let me explain this. They are very dense in their wording here and throughout this entire paper. So The the over a mountainous terrain, you get slope winds because the isobars are not in line with the isotherms. So you have different parts of the air being heated differently with different properties, which then creates changes in pressure, which then creates winds. That's what they said there. These flows react very quickly on the timescale of minutes to changes in the sensible heat flux at the surface, and they are almost invariably turbulent. Turbulence is generated over slopes mostly by buoyancy effects due to the day and by wind shear at night. It's really amazing how, depending on the time of day, you get two different driving factors. So it's either buoyancy effects during the day, which is due to differences in densities, or by wind shear at night, which is when you have differences in velocity in winds. It can be negligible or absent only in short periods in weak synoptic flows, for instance, during the morning and evening transitions of the daily cycle or overcast skies. So, in other words, you only really not get turbulence when you have morning and evening transitions. So, like when the sun is setting or sun is rising, or under overcast skies. In the past, nocturnal downslope winds have been investigated much more extensively than daytime upslope winds. Upslope winds are harder to measure and to simulate than downslope flows because they extend to a high altitude above the ground and they contain a wider spectrum of convectively driven scales of motion. So, in other words, the upscale flows contain much more variable wind patterns than downslope winds. So that's an interesting distinction there. So for those of you who are watching this video, you can see that I'm skipping through quite a bit of this paper because it is, as mentioned, a really long paper. If you want to read it yourself, you can look in the description. Otherwise, you can just listen here. I'm going through the highlights. There are other interesting parts, but these are mainly the highlights and how they relate to like boundary layers in general and the addition of thermodynamics to these boundary layers. So let's talk about valley winds. So in figure 2, along valley winds, so winds that are going along valleys develop as a result of the larger amplitudes of the daily temperature oscillations in the atmosphere of a valley in comparison to the atmosphere above a plain. So what they're saying is these winds develop because there are greater changes in the daily temperature in valleys compared to over plains. So that makes sense because differences in temperatures often result in differences in pressures, and that can result in driving winds. So these winds mainly occur even if the daily temperature range at the floor of the valley is not larger than over the plain because the pressure field at the surface is affected hydrostatically by heating anomalies. So in other words, differences in heat fluxes do have local effects which then drive winds. Valley winds, actually I should mention here, maybe a good way of describing winds in general is that they really just occur when you have imbalances in the system. So whether that's pressure or temperature or density. So valley winds can also arise because of temperature differences between air columns located at different points along a valley's axis. So again, just differences in certain properties of the air will drive winds. So thermally driven winds in a valley with a horizontal floor is seen in figure A. During the daytime, the atmosphere in the valley is warmer than over the plain. The largest imbalances in the pressure are often found near the mountaintop level. Horizontal pressure differences result quasi-hydrostatically from the vertically integrated temperature balances. So horizontal pressure differences, so when you go, let's say you move 10 meters to the left, you get a difference in pressure. They are often result because of temperature imbalances, is what that means. So the winds respond to the pressure gradient and it's accelerated by friction near the ground. That makes sense. So compared to slope winds, valley winds evolve over longer timescales. The pressure gradient to which the up valley flow responds is established in a few hours. Normally it takes about 6 hours before an approximately steady state is reached. The surface wind itself it reacts to changes of pressure gradients within a timescale of 30 to 45 minutes. So there are two different timescales. So let's talk about the convective boundary layer over mountainous terrain. The convective boundary layer typically has a simple 3-layer structure over flat and homogeneous terrain. So going from the bottom to the top, you have the surface, the mixing part, and the entrainment part. So the surface is right near the surface, obviously. Then you have the mixing part, which is like next bit up. Then you have the entrainment part, which is between like our boundary layer and the free stream flow in the Earth's atmosphere. Due to the interaction between flows at different scales, e.g. the valley winds, slope winds, the overall weather pattern, the convective boundary layer over mountains has an altogether different structure. So in figure 3, we can see it. The present discussion is limited to two specific aspects, namely the interplay between advective and turbulent exchanges and the definition of the vertical extent of the convective boundary layer over mountains. The transport of near-surface air by thermally driven winds towards the mountain ridges and then upwards over slopes is often referred to as the topographic or mountain venting. So let me just explain this. There are a bunch of different ways that wind can move effectively. And they have 3 different ones here. First of all, they talk about the mountain venting. And this is where you just have wind going up a mountain. So the upwind slope, the upslope wind, sorry, and it just goes up over the mountain. That's mountain venting. Unlike drafts over flat terrain, which follow a random pattern dictated by the dominant mode of convective instability, the updrafts responsible for mountain venting are anchored to the prominent orographic features, so in other words, to the macroscopic weather patterns. Thermally driven convergence enhances vertical transport right over ridges, possibly also initiating moist convection. So in other words, when you have thermal differences, then you can get different convection happening, and this results in something called MCV, which is the mountain cloud venting. So they go into clouds. And this is often when you see, I thought then, it's probably like when you see videos of clouds jumping up over a mountain, that's probably mountain cloud venting there. I'm not completely sure because I haven't looked into this properly, but I'm quite certain just thinking about this now, that's really what it could only be. Because of mountain venting, a deep layer of the mountain crest is affected by daily variations of atmospheric properties such as moisture, pollutants, temperature, or turbulence. Studies have shown that pollutants and moisture can be transported vertically for more than 1,000 meters above mountain tops. Wow. So this mountain venting can just push all this different material 1,000 meters well above the mountain tops. And I'm guessing depending on the mountain, it could be even higher or not as high. It depends on the mountain's height to begin with. Turbulence advection. So this is where you're literally transporting turbulence to another part in the flow. So turbulence advection towards an elevated layer around the ridge height may also contribute to a reduction of atmospheric static stability, thus enhancing vertical mixing. Besides the vertical exchange, thermally driven circulations also affect the horizontal exchange. So you have the vertical exchange, which is between two altitudes. We also have horizontal exchange, which is between 2 locations, left, right, front, or back. For instance, at low levels near coastal mountains, sea breezes and upwind valleys often superimpose and enhance the horizontal inland transport of moist air. So one thing that I should just mention about here with mountains near coasts, this is actually it's a perfect way of keeping in pollutants. So what happens, like for example, in LA, I remember learning about this a long time ago, but what happens is you have all these cars driving around. And because you have mountains fairly close to the coast, it's not very close, but it's close enough. All these pollutants that are being given out by these cars, they are around the surface, and then the flow that's coming from over the ocean then engulfs it, goes over the top, and like keeps all the smog in. So that's because of the mountain ranges, because the air that was originally over the city can't really escape before it gets flanked. So at high elevations over ridges instead, the above-mentioned mountain venting can locally increase humidity and aerosol content, generating horizontal gradients of these quantities. In concert with horizontal advection by means of wind, these horizontal gradients are responsible for advective venting. So that's the third type of venting. We're talking about mountain venting, which is when you have just flow going over up the mountain slope, and then it shoots up. You then have mountain cloud venting, which is where the flow goes up again, but into a cloud. Then you have the third type, which is where you have the venting goes horizontally. So you're over the mountain, and then the flow can just move around and transport these properties in that horizontal direction. Because of their thermal structure, elevated mixing layers can considerably influence the growth of ground-based mixing layers over the surrounding lower terrain or over a valley. Evidence of multiple layering is often found in the atmosphere near complex orography and ground-based mixing layers. So this is the final part of this podcast. Another horizontal exchange process was identified near the floor valleys of a curved axis. So what this means is in valleys, there is another type of horizontal exchange process. Horizontal airflow along a curved valley is subjected to centrifugal acceleration. So as you go along a curved valley, obviously the flow, like the curvature of the valley is trying to like throw the air to one side. That's the centrifugal acceleration, which can cause cross-valley flow. So that's pretty amazing. You have flow going from one side to the other of the valley because of centrifugal forces. During daytime centrifugal cross-valley flow, during daytime, centrifugal cross-valley flow can alter the development of the convective boundary layer. Near bends in the valley axis, the relatively cold up-valley flow is pushed towards the outer slope. Consequently, isotropes are displaced upwards near the slope. Since the resulting cross-valley pressure gradient does not balance the centrifugal force exactly at the heights, local imbalances drive a secondary cross-valley circulation that brings air from the outer slope to the inner slope near the valley floor and the opposite direction aloft. So in other words, you get this, like because of centrifugal forces, you have all this air rushing from one side to the other of the valley, but then because you have pressure gradients which don't balance properly, you have air flowing from the other side, from that side to the other side again. So you just get this mixing going on. So you not only have all these different types of flow that can result, you also now have two more types, which are convective, which are centrifugal driven and pressure driven. So that's all we're going to cover in this podcast. And I think you can agree that we covered quite a lot of dense information. And that's why we're stopping it here as well, because I think we'll need another podcast to go on from here and talk about additional boundary layer formations over mountains. We covered, for example, mountain venting. We covered thermodynamics of heat coming in and out of the earth. And in the next podcast, we'll cover the rest, which is like a bunch of different mixing types over mountainous terrains. So that's this podcast. Make sure to like, subscribe. And if you want to get better at theory, so we're going through theory here. If you want to get better yourself, check out our courses in the link description. And if you want to get better at CFD, check out our courses as well. And if you want to make your experiments 2 to 4% more accurate, then check out our Atmosphere Hawk. The reason why it makes your experiments 2 to 4% more accurate, which is most people don't realize, most aerodynamicists don't realize that their experiments actually have 2 to 4% error in them already. They don't realize it because they don't measure the density of air. And density of air does change from day to day and within a day. So we've been talking about weather patterns here, how temperatures and pressures change throughout the day. That affects the density of air. And the regular day, it's about 2 to 4%. Between days, it could be more. Between weeks and seasons and months, it definitely is more. It can go up to like 15% quite easily. So if you're not measuring the density of air in your experiments, you have that error in the experiments without you even knowing it. That's probably why your experiments aren't giving you as good results as you want or as repeatable results as you want. That also makes your CFD validation much harder because let's say you're measuring your experiment at a density of 1.2 kilograms per meter cubed, which is ideal. But then in your CFD, you might have 1.225, which is the other standard that people use. Or you may have just difference. Like, for example, in your experiment, you might have 1.16 kilograms per meter cubed. And in your CFD, you put it at 1.2. You really don't know. And that's going to result in differences in Reynolds numbers, differences in forces, differences in turbulent breakdowns and turbulence, and difference in vortices, their breakdowns, their formations, all of that. So check out the Atmosphere Hawk, gets rid of all those errors for you. And I'll see you in the next podcast. Peace out, amigos.